Yeah, you don't have to apologize about anything. Actually, I find it kind of a relief because I just go in there and just go, and I don't have to worry about stuff as much as I used to.
I guess that's true, but at the same time, when students perform poorly, it reflects on you, and
Well,
it's clear that it's not you, it's an effort thing.
yeah.
So I feel bad in that regard.
Oh, well, if that's the case, I've gotten myself past that a little bit, So since we're doing that, I'll tell you what, you're engineering physics, right?
Yeah.
So I'm gonna move ahead one chapter. I was gonna work one problem today, and then next time I was gonna do the energy stuff, but I'm gonna do the energy stuff this time.
Oh, great.
But I think, well, let me just see because the reason I do that, a reason I'm switching, is because, as a, I try not to say this honestly, but physics majors are kind of taught things in a more correct sense, and engineer, you got to kind of somehow get them to go down that same path. And this book is written kind of semi correctly, but it's confusing to a lot of. Let's see if I can find it. There's the dynamics. Okay. Oh, good. It's listing it in chapters. No. Oh, there it is. So in this one, they start by doing movements of the particles and stuff like that the same way that you probably do in physics. Then they break it into two sections. And what I like to try to do, is, and I think I'll do it through just working a problem, is combine both of the concepts. Because they're actually the same thing. Let's see, does that one have a friction? I can kind of, here. I kind of can see it, but at the same time I can't see it very well. Oh, it looks okay on the board. Now, which one would be a good one? I don't know. Well, here. Wait, this one has no friction though. I'll do two of them. I'll do one with friction and one without. That's a good no friction. Let me move on to the next thing. See if those are too easy for. But then maybe I'll do that one too. That one has friction. And then what I'll do is I'll mess with this one. So I'll start with that one. And then at the same time, if I do this, and then make it go across part of the screen so that, gosh, I can barely see that. Okay, that leaves half the board open. Okay, so I'm going to do this one. Then I'm going to, these lights never work right. And then I don't know what I did to make it work, but that time it worked. Okay, so it's got a 5-pound collar pulled by a cord that passes around a small peg, because that's the peg. Oh, it says it's the. If the cord is subject to a constant portion of the collar at rest, is at rest at A, determine the speed. Okay, so it says neglect friction. It doesn't necessarily say that there is no friction. Then it says determine the speed it reaches at B. So, okay, physics, y'all had the T and the U, remember that kind of stuff. In my mind, I don't toss them in the trash can. And then there's the V as well. I don't toss them in the trash can. But, okay, so this is one thing about Thermo that Thermo does a good job of. And what it does is it talks about, you know, in this case, he doesn't have a number for the state. So, state one at some time, whatever, and it goes to state two. And the way I work these problems is kind of like, what types of energy can show up? And of course, there is no spring, but it doesn't really matter. So what I generally do is I say, all the types of energy that could show up, you got the potential energy of moving up and down. That one doesn't exist. I'm assuming that gravity goes up and down. I mean, I guess it's a reasonable assumption to assume that all the time. Then you got, I guess I could do that one next. Depends on, I'll say a question mark because that can depend. Some books have delta, some books have x squared, some books have other things. And then you got, of course, this is part of the thing where they type it, you know, so these are potential energies. And then the next kind of common, I guess, the next common one would be kinetic energy. And then there might be some other ones, but then you also have an F dotted with, I hate to use X, so I think what I'll do is I'll go back to this being the deflection of the spring, and I'll say X. And then what I'll do is I'll turn and say, you got the energy from lifting it or dropping it. The energy from it being pushed against the spring. There is no spring. You have the energy of it moving at a certain speed, kinetic energy. And then you got energy which actually this is used to derive those two. So you have to be careful that you don't include the spring here, because if you look at the spring, you know, F and X, and you think to yourself, okay, what's the energy here? And this thing is F is equal to Kx. If you look at the area under there, you got that. If you're at some location X, and this becomes F is equal to Kx. So if you look at the area of the square, you get Kx squared, and you only take half of it, so you got your energy out. So actually, this can be derived, that can be derived from that. So this is okay and used for everything, but let's say, I'll say springs. That's not even how you spell spring, but I don't have room to put the end back in there. Or movement up and down. I don't know what else to say. Since this was used to derive that works for everything. Don't do it again because you already have a spring there. And mg is easy. Mg is equal to the weight. So if you let the weight drop down, a certain, like y, which I guess I should use h, then the weight times the distance means that it's this can be derived from that. So, you know, so then you just look at the state 1 and state 2. And even if there's not a spring, or a movement up and down, I always put them in there. And then sometimes they'll write, depends on the notation, they'll say either 1 to 2 or something like that. And then you just look at the ending state. And I know there's no so you kind of had energy, then you had added or subtracted energy, and then the final energy.
Are you streaming right now?
Yeah, it should be. Am I? I hope so. Oh, I got a notification, let's see. Oh, there I am. I sometimes bring this, uh-oh, I don't hear myself though. Oh, there we go. Oh. It's usually about a 5-second delay. So, but if you have questions, that's okay, or comments. Because I know in physics, y'all combine these two and then this one, and then you look at conservative forces, and then what is that? That's part of this T plus U is equal to T plus U, but then you got a situation where, and he does that in the book, but you have a situation where, let's see if that's still, where did it go? Did I drop the book out? Oh, there it is. Oh, I don't want to roll backwards because then I'll mess up where I'm at.
You could probably duplicate the tab and then scroll up.
Oh, there you go. Maybe I can do that. Just cheat. Do it twice. Oh, now wait a minute. Did I? Now, if I go up, let's see what happens over here. Oh, good. Okay. So this is kind of weird. Not weird in a bad way. Okay, I think I went too far back. Yeah. 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 Okay. There we go. Because what he does, he starts off with this, and he starts to work at the force. Then he goes in and he does this bit. He talks about the dot product has to go in the direction. Then this is where he's talking about the work of the weight. That's probably the way I should have said it. So he finds out, that going from 1 to 2, you get that. And then somewhere, okay, so here's your springs. Okay, then he goes off and does it. Well, this is the first time. Okay, so I should have written it differently up there. But, so you got that. And all along during this period, he's okay or comfortable with friction. Because that could be put in there. Okay, but then, here, I'll shrink back. He gives a set of problems, which that's where I'm at in that problem. He goes to the next section. Okay, well first, then he goes to power and efficiency. Then he goes, that's a little short section. Then he goes to, and I wrote that wrong because he goes to conservative. And he goes in, it's kind of the similar thing. It's just presented exactly the same. It's just conceptually, this is kind of common in the, so I wrote it with the U, I should have wrote it with the V. Sorry about that. So that was illegal. So that's what y'all are probably most used to. But, it's the same thing. It's just, to me, I like to do them all at the same time and ignore the notation just to get through, because that way I don't have to worry about which one I'm doing. I just start working on one.
We do the same thing. We just tend to draw little diagrams, free body diagrams for everything, and then by looking at that, we can see what forces are acting in the x direction and what forces are acting in the negative x direction, and the y and the negative y.
Oh,
and we can
okay.
write the equation just from looking at that.
Oh, okay. So it's similar. Okay, so this is nothing really new to me. And in this case, okay, so I guess I could write down 0, and I can write down 0 here because he said it started from rest, I think. Yeah. When it's at A, okay, A is back here. And then, oh, it doesn't move up and down, so it's 0. Doesn't move up, it doesn't have a spring, so it's 0. So you get this, 1 to 2, F, well, I'll just leave it in there with the X. That's not generally you put a D right there, but, here, I'll tell you what, I'll do it this way. There we go, that's probably more efficient. And then, the key is the geometry here. And what happens is, if this is 4, and that's 3, then the distance between here and there should be 5. So that's 5. So then by the time it got here, the rope, in other words, if you painted, I don't have a funny marker, but if you painted a spot on the rope right there, and then you pulled it, that spot would move to, okay, 3 minus 5 is 2, right? Then move 2 down here. So technically, since the movement of this dot is this direction, and the force is that direction, they dot together to give you a positive, and they dot to give you 10 because it's constant, times 2, give you this 20, and then you get half M, which I don't remember what it was, 10 pounds, which I don't know what that is, but B squared, and then you square root it, all that sort of stuff. So there's nothing really fancy. 2 times, well, take the 10 across, so you get a 2, then bring that up 4, get a 4, and then get 4. I don't know, that's some kind of number. But that's not, you know, that's not that hard. It would be hard, though, if you had friction. If you had friction, then your hardness becomes really bad because you'd have to take the component and then you'd have to integrate, taking this as the normal and this friction force. So whatever this force is, you'd have to integrate this from whatever angle that is to 90. And then watch the friction force. The friction force would start at something. At this point, all the force is pulling that way. So you're going to have the largest friction force back here. So you're going to have, when it comes to adding friction to that, you would actually have a true integral. And you'd have to F dot dx. But now this x would have to be, so it's doable, annoyingly doable, but you have to take the integral, you have to find this component, find the angle. This angle would be the same. This would be the normal. And then you'd multiply that, so you'd have to integrate that from whatever angle that is up to 0. So you integrate from whatever, or you could take this angle, and then you could integrate that from whatever number that angle is to 90, it's up to you. But just express that, then that angle is this angle. That would be not so fun, because you'd have an integral in there. But this one is more doable. There's one later that's not even close to doable if it had friction. So, let's see. Well, maybe there's something more interesting. I don't know. Let's see, go down. Oh, here's an interesting one. And plus it's on the right side. Oh, that's the one I was talking about. So I guess I could do that one and then this one. But if I do that, I need to move the cover to the right side. And yeah, That'll do, Frank. So this one you can do the same thing, but like I'll cheat and use, because it fit right in there, amazingly enough. It's just all the numbers will be different. So you got a chord subject to a constant force. Now, I found out that from about right here, about right there, you can't see because of the, oh, you can't see because it blocks. So what I'll do is I'll turn over to the, I can turn it over and stream off of the monitor for half a second by cutting out, aha, so cut out the video display. So now they can see, streaming, they can see the entire monitor. So they see this, which is the chord subject to a constant force of 300, which is good that it's glad it's constant. 15 kilogram smooth collar. Now, if this one were, if this one were rough, it would be really tough because then you'd integrate from here to here, and then through this arc, you're going to have some frictional force that is going to be awful, going constantly in the negative, or constantly against retarding the motion. But, you know, if you start right here, and you're pulling the force that way, it's easy to break it into components here, but when you get up to here, and you're pulling it that way, you'd have to maybe have polar coordinates from here to here maybe, or something. And then you have a third set of problems where your friction would slow you down here. So you see how this one would be awful, whereas the other one wouldn't be so bad. Okay, so let me switch it back so they can see. They've seen the problem. Now, display capture, was that it? No. Wait. Okay, video capture, there we go. Yeah, now you can see part of the board that gets just clipped by this. See, I learned that. So there's part of the board that, and the other ring's the same way. Except it's a different part. It's up on the right side. But I figured out how to work around that. So there is no spring at all. So I'm just going to take it off consideration. I'm not going to arc it out because I may use the equation again. And then I go from state A. Did he say state B? Velocity, okay, velocity when it reaches point B. Okay, so he starts at A, which I'm assuming A is that point. So I'll set up a datum. And me, I like to pick the lowest spot, because in that way, you know, it just becomes easier.
Is the collar not the cylinder detached? So wouldn't it start from where it's completed?
Yeah, I think what they're saying is it started down here and it caught it in mid-motion. Because he only gives me my measurements to there. He doesn't tell me where I'm at there.
Sure.
That's what I'm guessing.
Sometimes the diagrams are
yeah.
This I think with the
Yeah, it can be bad. And you would think after years that, but
I just don't understand like the practical usage of this scenario. That's what makes it even more difficult to decipher.
I never asked the practical application of these. But that's bad. But, you know, one of the things is you can find practical applications of stuff like this, but I don't know, like moving reels, you know, those are kind of cool because but they're not used anymore because it's all digital. But it goes in and there's a mechanism that pulls the thing through, things like that. But this, I'm not sure. maybe there's a bunch of people down here pulling, or there's a truck, here you go. And they're trying to lift this, here's the truck, I don't know. You can dream up all sorts of stupid things that would be used. And, oh, I know, there's a bale of hay connected to this, and his barn sits here, and this is where the bale of hay goes in. I don't know. And he goes fast enough so that when he stops, the hay goes straight into there, just flies into there. I can't figure out a practical application of anything. I've been stuck here long enough, there is nothing practical, so. So, since I put my datum at A, okay, I'm gonna call this state 1 and this state 2. Then this has a 0. Does he say it starts from rest? Yeah. So this is 0. So all I get is the application of the load, and what I'm gonna do is I'm gonna do it this way, F dot X from 1 to 2, or if you like it better, from A to B, equal to. Now, there is no spring, so that was gone, but this time, some of your energy gets absorbed into the potential, adding potential to the thing moving up. So then the question is, first question is, it's 15. Well, let me write it in symbol form first. MgH2. These are the non-zero parts. And then 1/2 mv squared. And so that's all I've got. So then if you look at it, I'll deal with the F dot X in a second. But then the M is 15 kilograms. The G, 9.81. The H is, okay, 300, or 0.3. I'm going to use meters, so 0.3 and then 0.2. So I'm going to use this as meters. Because this is kilograms, this is meters second squared. Did I get all those? M, G, and H, and then another 1/2, and then the same M, and then you don't know the V. Right? That's what he wanted to know. And so now the question is, what happens here? And he says, it's a constant 300, but the same thing occurs. Two ways you can look at it. What's the distance from here to here? And now we'll have to ignore the size of the pulley and say it's a dot pulley. That means you got a triangle, goes here, and how wide is that? 200, and then another 200. I'll just say 0.4, and then all the way to the top goes to 0.5, and it looks like 0.7 meters from the top to the thing. And so that's not, that I can think of, it's not like a 3, 4, 5 meter thing. So the rope length, let's say the length of the rope at state 1 is going to be square root, okay, I've already forgot, okay, 0.7 squared plus 0.4 squared. And the length of the rope when you reach your final state, so the rope will go from here to there, point pulley again. So that's a 200, 200. So 0.2 squared, 0.2 squared is 2 times, oh, I'm sorry. Well, we'll just leave it like that. And so a spot that you painted on the rope here moved out here how far? And so it moved a certain distance, and it moved that distance, x, in the same direction as the F. So then that distance it moved would be 0.2 plus 0.4 squared minus, I guess I could do 2 or square root. No, I'll just leave it. No, I'll just leave it. It's 0.2 times, but I'm going to leave it. 0.2 .2 squared plus .2 squared. I have no idea what that is. It's gotta be something reasonable. Turn it sideways, hang on. I'm not very good at this calculator. 0.7 squared.
I got 0.523.
Oh, good, you're way back. 0.523. And so that's it. I mean, essentially, now you've got 300 meters. Pulling that distance, you've got 300 times 0.523 meters that it pulls it through. 15, 9.81, 0.5, plus 1/2, 15 would be squared. So now you just put these all together, and then do all that, take the square root, and that gives you your report. But again, if this had friction, this would be an awful, hideous problem, because you would have to find the normal component here, multiply it times mu. That normal component would change as you got pulled up. It would be doable during this section, but when you erase that, it would still be doable, but it would be just awful.
Yeah, I remember doing arc with Ken Calhoun.
Oh, do you?
I think it would be similar in nature.
Yeah, because you'd have to integrate, and then you'd have to figure out, you'd have the complexity of a vector going to a common point, broken into an R in a theta component, which you don't care what the theta is, but you do care what the R component is. And then, so that's why they don't do that in this book. Although it would be intriguing to do. It would be intriguing to do it once, to say you knew how to do it. Oh, it's 9:45. Well, I'll do that one next time. So, but I'll go ahead and drop the string map. Again, I'm sorry. I'll tell everybody online too. I'm sorry I started late. They put cones up and stopped me from entering the campus.